2.4, the quotient rule. The quotient rule gives the derivative of a function that is the quotient of two functions. So when we talk about quotient, we're talking about the answer that you get from something that's divided. Okay, so divided. So we're looking for a fraction. Okay, so the quotient of two functions is derived from the product rule. Okay, so this is the quotient rule. So if h at x equals some function f at x over some function g at x, then the derivative h prime at x equals, so it's very similar to the product rule, a little bit different, derivative of the first function times the second function, but this time we're actually putting a subtraction between them. So minus the derivative of the, and I like the numerator function, sorry, just the numerator function times the derivative of the denominator function all over the denominator squared. Okay, as long as the denominator function doesn't equal 0. That would be the restriction on the domain. Okay, in Leibniz notation, if we're differentiating d by dx of u over v, what we're going to do is we're going to find the derivative of u times v minus u times the derivative of v all over v squared. My short form way of doing this, and you'll see this a lot in university, oh, it's not uv now, it's u over v prime. This is going to be u prime v minus uv prime over v squared. This is the one I use. It's very common, okay, because it's the short form and it's quick to write out rather than dealing with d by dx's, du by dx's, okay, and or f at x's. So let's jump right into this. Determine the derivative of h at x equals, and then we have two functions here. We have 3x minus 4 in the numerator, and then we have x squared plus 5 in the denominator. So if we want to formally set this up, we could set up the numerator as u and the denominator as v. And if you want to do the work on the side of your page, u is 3x minus 4. But then if we derive, so du is going to be 3. Right, derivative of 3x minus 4. Derivative of x is just the coefficient. Derivative of a constant is 0. Then we're going to have v and dv. So x squared plus 5. Derivative of x squared, you bring that 2 down, we get 2x. Derivative of 5 is 0 because it's a constant. So now we can go ahead and sub this in to h prime at x. So u prime, which is du. Oh, you know what? Let's change that to u prime. I like u prime better, and I like v prime better, because then we don't have to put what we're differentiating with respect to. All right, so u prime is 3, and then v, as it is x squared plus 5. Minus u, which is 3x minus 4, times v prime, which is 2x. Okay, and this is all going to be over v squared. So our v is x squared plus 5, and we're going to square that. Okay, this right here is the derivative. That's it. If you wanted to simplify this a little bit more, we can distribute the 3 into the bracket to get 3x squared plus 15. And we can distribute this negative 2x into the bracket. So negative 2x times 3x is going to be negative 6x squared. And negative 2x times negative 4 is going to be positive 8x. Okay, and if we collect like terms in the numerator, 3x squared minus 6x squared, I get negative 3x squared. Okay, plus 8x plus 15. And this is all going to be over x squared plus 5 squared. And it's very common just to leave the denominator as whatever it is squared. Example 2, determine the equation of the tangent line to this function here at x equals 0. Okay, so this is a rational function. So we're going to call the numerator u and the denominator v. So let's write out u is 2x. Okay, and let's solve for du. So the derivative of 2x is just the coefficient, which is 2. And then we have v, which is x squared plus 1. Derivative of v is going to be 2x. Right? Derivative of 1 is just, this is just a constant, so it's 0. So let's go ahead and, because this is in y equals notation, what we have to do is we have to actually write this as dy by dx. Okay, so as a reminder, u over v prime is u prime v minus uv prime over v squared. So u prime, which is 2, bracketed v, which is x squared plus 1, okay, minus u, which is 2x, times v prime, which is 2x, all over v squared. So v is x squared plus 1. And then square that. Okay, so when I'm doing a question like this, I don't usually simplify because we're finding the equation to the tangent line at x equals 0. So that means what we're going to be doing is we're going to be subbing in x equals 0. I am going to simplify just one more step just for practice, but you are risking that you're going to make a mistake. So 2 times x squared is 2x squared. 2 times 1 is 2. Negative 2x times 2x is negative 4x squared. Okay, and that's all over x squared plus 1 squared. Okay, so dy by dx, 2x squared minus 4x squared, I get negative 2x squared, and then plus 2 all over x squared plus 1 squared. Okay, let's sub in x equals 0. Put an at there. Okay, so this is our slope. This is the formula for slope, a slope of our tangent line. Now let's sub in 0 because we're specifically interested in the slope at x equals 0. So negative 2 0 squared plus 2 over 0 squared plus 1 all squared. Okay, a lot of times when you're working with 0, it's really easy. 0 times anything goes away. We don't have to include that. Okay, and then 0 squared, we don't have to include that. So this actually simplifies very quickly to dy by dx equals this 2 value over 1 squared, which is just 1. So I'm going to delete that fraction symbol, and that's it. Okay, so the slope that we're dealing with, we can put m equals 2 if we want. Or we can say y prime at 0 equals 2. It's more of a grade 12 way to say it. Okay, so we're kind of going backwards here. That's okay. We're going to go on the other side of the screen. So what we have so far for the equation of our tangent line is we have y prime at 0 equals 2. Now we need the actual point. So we want to find the point where x equals 0 so that we have an x comma y. So let's just go y at 0 equals 2 times 0 over 0 squared plus 1. Well, that's just 2 over 1. Sorry, 0 over 1, which is just 0. So this point does go through the origin. Because it goes through the origin, which is x comma y, the y-intercept is 0. That means we don't actually have to plug it into y equals mx plus b. We can just simply state, therefore, the equation of the tangent at x equals 2 is y equals 2x, because this 0 would essentially be here. Example 3, determine the coordinates of each point on the graph of this function f at x, where the tangent is horizontal. Okay, so I'm just going to quickly draw and recall, like maybe just like a polynomial. Okay, so the tangent is horizontal when we have a turnaround point. Okay, and this is going to be a focus going into the next unit. Okay, so we have the tangent is horizontal when f prime at x equals 0, right? The slope equals 0, because then we get a horizontal line. So we have to determine the coordinates of the points where this occurs. So let's start with f at x equals 2x plus 8 over root x. Let's call the numerator u and the denominator v. Okay, because u over v prime equals u prime v minus uv prime all over v squared. So u is 2x plus 8, and the derivative of u is just 2. And v is, I'm going to actually write this as x to the 1/2. You can't really work with a radical when you're doing differentiation. Okay, and then v prime is going to be 1 over 2x to the 1/2. So let's go ahead and solve for f prime at x. We have u, which is 2x plus 8. Oh no, I apologize. U prime is first, which is 2. V, which is x to the 1/2, minus u as it is, which is 2x plus 8, times v prime, which is, instead of writing this beside, I'm going to write this over 2x to the 1/2. And this entire numerator is over v squared, which is x to the 1/2 squared. All right, let's simplify this a bit. So I'm going to write this as 2x to the 1/2. Now, in this numerator, the 2 can factor out. So x plus 4, that's what it would factor out to. So minus 2x plus 4, that's fine. I'll do this in 2 steps. 2x to the 1/2 over, and then if we multiply, because this is an exponent law, 1/2 times 2, we just get x. So at this point, I can go ahead and I can cancel out these 2's. And then if we want, we can divide these. So when we divide x divided by x to the 1/2, what we do is we subtract the exponents. So it's 1 minus 1/2, which is x to the 1/2. So far I get 2x to the 1/2 minus, if we simplify this term as x to the 1/2, then we're going to have to simplify this term. Because remember, this entire denominator is the x to the 1/2. So both the x and the 4 are over x to the 1/2. Okay? And we're going to leave this in brackets. Because remember, this negative sign still has to technically distribute into the bracket as well. Okay? So right now, what we're dealing with is 4 over x to the 1/2. I'm going to write this as 4x to the negative 1/2. And I'm good with that. So plus 4x to the negative 1/2. And that's all over x. Yeah. Okay, I'm going to keep simplifying. So we have this here, and I'm doing a lot of this work at the side of my paper so that this part can flow. We have 2x to the 1/2 divided by x. So we get 2x to the 1/2 minus 1. So we get 2x to the negative 1/2. Okay, so this is fully simplified. 2x to the negative 1/2. Now, if we distribute this negative sign into the bracket, we just get negative x to the 1/2. This needs to be divided by x. So we get negative x to the 1/2 minus 1. Again, we get negative x to the negative 1/2. And then this 4, but it's actually negative 4 because that negative sign gets distributed in. We get negative 4x to the negative 1/2 divided by x to the 1. So we get negative 4x to the negative 1/2 minus 1, which is negative 4x to the negative 3/2. Okay, the first two terms are like terms. If you look at those, we have a variable of x to the negative 1/2 on each of those. So let's go darker. F prime at x equals, so 2 minus 1 is just 1. So x to the negative 1/2 minus 4x to the 3/2. That is fully simplified. Now at this point, let's go back up to the question and let's reread it. So we're going to determine the coordinates of each point on this graph where the tangent is horizontal. So I think that it's important to actually simplify this, because if we were to have dealt with maybe one of the previous forms, maybe even the original form of the quotient rule, it would be really difficult to isolate an x. So now let's go ahead and sub in 0. We know that a horizontal slope is going to have the slope of 0. So this here means slope, f prime at x, and it equals x to the negative 1/2 minus 4x to the 3/2. Okay, this is a little bit difficult to me because we have two x values. So what I'm going to do is I'm going to factor out, remember, the lowest exponent on x. So what is a lower number? Negative 1/2 or 3/2? Oh, this is negative 3/2. Okay, so the lower one is negative 3/2. So let's go ahead and divide both of these terms by negative 3/2. And I get x to the negative 3/2. So I'm going to just deal with the exponents here. Negative 1/2 minus negative 3/2. So that's a plus. So 2/2, which is 1. Okay, so we have what's left in the first term is just x to the exponent 1. And then these two cancel and we have minus 4. So as of right here, we have two potential situations where we're going to have a horizontal slope. It's either going to happen when x equals 0 or when x equals 4. Okay, so if you think about the domain of the original, so f at x equals 2x plus 8, I'm going to erase this. So the original function has a domain that x is greater than 0, right? Because we have to put the restriction on this that the denominator has to be greater than 0 because the denominator is root x. Okay, we know that we can we can't divide by the number 0, but then also we can't have a negative number under the root. So we know that root x is going to have to be strictly greater than 0. And if we squared both sides, x is strictly greater than 0. So this x equals 0 is going to be inadmissible. That is not going to exist. So now let's go ahead and just solve for the point where the tangent line is horizontal, which occurs at 4. Okay, so 4 times 2 is 8, 8 and 8 is 16. I get 16 over root 4 is 2, so I get 16 over 2. which is 8. So I get the point 4, 8. So therefore, the tangent is horizontal at 4, 8. So if we go to Desmos and we graph the function 2x plus 8 over x to the 1/2, and again, this is going to be on the domain from 0 to infinity. Okay, if we zoom in, we can see that this here is the point 4, 8, and we're going to have a horizontal tangent at 4, 8.